Hello everyone, welcome back to physics-based animation. In the last video, we learned how to simulate 3D elastic objects like this bunny. In this lecture, we are going to learn about a more powerful tool for simulating deformable objects, the finite element method. The finite element method is really the go-to tool for physics-based animation. It's much more involved than mass spring system simulation, but mastering it is well worth the time. From the previous video, you might remember that the geometry of our simulated object, a bunny in this case, was composed of vertices and edges. And by storing mass particles at the vertices and by positioning springs along the mesh edges, we could arrive at a simulatable representation of this object. At first glance, this mass spring setup seems pretty ideal, but it has one crucial flaw. If we examine the space between our springs, denoted by this triangle, we realize it's just empty space. Now, we hide this problem via rendering, but really, in between each spring, there's no mass and therefore no material to store kinetic and potential energy. The bigger we make the space between our springs, the more empty space there actually is, and this doesn't really map to the structure of real-world objects, at least not at a non-atomic scale. Finite elements are going to fix this problem by assuming all this empty space is actually filled with bunny, and this is going to allow us to build more simulations that mimic more complex real-world materials. Everything we learn today is based on what's called the continuum hypothesis. Roughly speaking, the continuum hypothesis tells us that no matter how close we look at an object, like this rubber ball, it appears to have an identical homogeneous composition. In other words, this ball is made of the same rubber no matter how far we zoom in. Now, this model is not accurate at extremely small scales, but it's very useful for physics-based animation, which occurs at a much higher level. Continuum mechanics uses the continuum hypothesis to understand the motion of a deformable object. Essentially, continuum mechanics is interested in understanding how every point in a deformed object is moving. At a high level, our development of the finite element method will follow our development of mass spring systems. In learning about mass spring systems, we first chopped our bunny up into a collection of springs, then built a cohesive model by thinking about what happens to each spring individually. Similarly, for the finite element method, we are going to chop the bunny up into little 3D volumes and figure out how to treat each volume separately before reassembling them to arrive at a whole bunny model. Now, commonly, the shapes we work with in graphics are represented using triangle meshes, and each triangle is constructed by connecting three vertices. The problem with this representation, in the context of simulation, is that we want to simulate the volume of the bunny. That means we are going to need a different primitive to use in our finite element spring analog. We don't want to stray too far from what we are comfortable with, so we are going to use the volumetric cousin of a triangle, the tetrahedron. Filling our bunny triangle mesh with tetrahedra may seem like a hard problem, but luckily, there are now reliable programs that will do this for us. My favorite one, Tetrahedral, is available at the link shown here. While in 3D, a triangle spans a patch of surface by connecting three vertices, a tetrahedron spans a subvolume by connecting four vertices. Like with our mass spring system, we can store information both in the volume of the tetrahedron and on its vertices. One important thing we need to keep track of is where the tetrahedral vertices are in space at any time. We can do this by storing this position at each vertex. This is equivalent to how we stored particle position on mesh vertices for mass spring simulation. And because these per vertex positions can represent any shape, any configuration our tetrahedron can take on, we use them as our per tetrahedron generalized coordinates. Again, this should look very similar to the mass spring case, save for the fact here Q is a stacked vector of 4 3D positions rather than 2. We can also take the time derivative of our generalized coordinate to get the generalized velocity. We end up with a stacked vector of our per-vertex velocities, which, unsurprisingly perhaps, is also analogous to the mass spring case, save for the number of vertices involved. Okay, now we need to figure out how to actually deal with the material occupying the volume of our tetrahedron, and this is really the meat of the finite element sandwich. In order to make some progress, let's simplify our problem a little bit. Rather than worry about our tetrahedron moving all over the place, let's just look at a tetrahedron fixed in space. I've represented the fixed position of each vertex using the letter capital X. Imagine I tell you the value of some as yet unknown function on the vertices of this tetrahedron. The game is to reconstruct the function at every point inside the tetrahedron. Let's make a choice about how to do this. Specifically, we are going to represent the function at any point inside the tetrahedron as a weighted sum of the per-vertex values. The weights for this average are going to be spatially varying functions, denoted by phi sub I, and there's going to be one associated with each vertex. Typically, we refer to these weight functions as shape functions. So what are these functions? How can we find them? Well, let's see if we can compute them. Now, our tetrahedron has position values at each vertex. Let's say we approximate this position function at some point in the tetrahedron capital X. It would be great if the approximation returned the exact same point. Maybe we can use this insight to actually compute our shape functions. Let's unpack the vector equation from the previous slide into its scalar components. Rearranging, we see that we can view this as a system of 3 equations, one for each component x, y, z of the position. This becomes more clear if we assign standard linear algebra labels to each component of the equation. Here, our shape functions, the phi i's, are our unknowns. It becomes immediately clear that there is a problem. We have 4 unknowns, but only 3 equations. We can fix this by adding one more equation. Let's add a constraint that at any point in the tetrahedron, our shape functions need to sum to 1. Now we have 4 unknowns and 4 equations, so let's try to solve this thing. We can use our new equation to eliminate one variable from our system. In this case, we will decide to set phi sub 0 to be 1 minus phi sub 1 minus phi sub 2 minus phi sub 3. Now, via direct substitution for phi sub 0, arrive at the following system of equations, which introduces the matrix T. Each column of T is an edge vector pointing from capital X0 to another vertex in the tetrahedron. Again, this follows directly from algebraic manipulation. In most cases, really unless our tetrahedron is degenerate, so unless it's been squashed flat, we can solve this system, and the solution looks like this. Now for any position capital X inside the tetrahedron, we can compute values for phi sub 0, phi sub 1, phi sub 2, and phi sub 3. You may have noticed by now that these shape functions are the so-called barycentric coordinates for our tetrahedron. These shape functions are going to take values between 0 and 1 inside our element, and by inspection we can see that they are linear in capital X. Essentially, we are saying that we will reconstruct functions inside our tetrahedron using linear interpolation. That's all well and good, but we sort of lost track of the plot here. The game, the real game, was to understand how all this works when our tetrahedron is part of a deforming object. Fortunately, we can use the tools we've just developed to sort that out. Let's go back to where we started, our undeformed tetrahedron. We embedded this tetrahedron in 3D space via its per-vertex coordinates, the capital X's. We are going to give this particular 3D space a name. We'll call it the reference, or undeformed space. In this space, our tetrahedron takes on its undeformed shape. The undeformed shape is analogous to the rest length of a spring. It's the shape a chunk of material takes on in the absence of all applied forces. Now let's bring back our time-varying vertex coordinates. We can think of these vertex coordinates as embedding our tetrahedron in a second 3D space. This space is the world, or deformed space. This space represents the 3D world you and I occupy. Each vertex has both a reference and a world coordinate, which establishes a mapping between these two spaces. Next, we will use this per-vertex mapping to establish a mapping for every point in our undeformed tetrahedron into the world space. And this will allow us to formalize the notion of deforming a single tetrahedron. Luckily, we already worked out how to rebuild a function inside a tetrahedron using values at the vertices. Now, for any point in our undeformed tetrahedron, we can figure out its world space or deformed configuration. Rather than carry this summation notation around, it's convenient to represent our reconstructed world space coordinates as a matrix vector product. Here n is a matrix of shape functions which multiplies our per tetrahedron generalized coordinates. Now we have all the pieces we need to turn our variational mechanics crank. We'll start where we always start, by computing the kinetic energy of a single tetrahedron. Let's compute the kinetic energy for a single point in our tetrahedron. At first glance, this formula looks a little different from our previous version, but it's actually the exact same. We can already see that we need the length squared of the velocity at our point capital X. The major missing piece is the mass. We are going to build the mass at a single point using the density, which is a property of whatever material we are simulating, and the infinitesimal volume surrounding our point X. However, this is only half the battle. We need the kinetic energy for the whole tetrahedron, not just one interior point. We can compute that by integrating this kinetic energy over all the points in our tetrahedron. Let's develop this formula further so that we can express it in terms of our generalized coordinates. We'll just do our usual thing, which starts by expressing our squared length as a dot product. Next, we need a formula for computing the pointwise velocity of our tetrahedron. We already have a pretty compact expression for the time-varying deformed position. We can compute the velocity via time integration. One of the advantages of this finite element setup is that the shape function matrix is only a function of the reference coordinate, not time. Only the generalized coordinates, the deformed vertex positions, are a function of time. This makes our time derivative pretty simple to evaluate. Just like any other function, we reconstruct the velocity inside our tetrahedron using our shape functions. Now we can substitute this definition of velocity into our kinetic energy formula. Note that q dot is not a function of the reference coordinate x, and so we can take this out of the integral. And the integral sandwiched between our q dots results in a 12 by 12 matrix, which we can call m sub 0. And this is the per tetrahedron mass matrix. The only thing we need to figure out is how to actually compute it. This is a pretty nifty integral, as it integrates a matrix equation over our tetrahedron. Let's start by expanding the integrand, which we see is just made up of products of our shape functions. We compute this integral by integrating each term separately. Here, we assume our density is constant inside the tetrahedron, so we also remove that from the integral. We are left with the problem of integrating the scalar product of shape functions over our tetrahedron. Now, integrating over a tetrahedral domain looks like it could be trouble, but fortunately, there's a closed-form solution for such integrals using barycentric coordinates. Here, vol is the volume of our undeformed tetrahedron, and we can see that our integral just multiplies the tetrahedron's total mass. You might have already noticed that phi sub 0, or the first barycentric coordinate, is not present in this equation. That's because it is completely determined via the values of the other barycentric coordinates. Every time phi sub 0 appears in an equation, we simply eliminate it with this formula. Let's look at an example of integrating one term of the mass matrix. We have three integrals to evaluate, and we do this from the inside out. So step 1 is to integrate with respect to phi 3, the result of which is the following. Next, we integrate with respect to phi 2, which leaves us with this term. And finally, we integrate with respect to phi 1, which gives us our answer. We simplify a bit and arrive at the solution 1/10 of the total tetrahedron mass. Now we can fill in the entire mass matrix by evaluating the remaining integrals. You can do these by hand, of course, but typically one uses a symbolic integration package like MATLAB's Symbolic Math Toolkit to expedite this process. Just like for our mass spring system, we need to take this single tetrahedron mass matrix and use it to create a mass matrix for our entire bunny. We can do this using the generalized coordinates for the whole bunny tetrahedral mesh, combined with the generalized velocity. Just like with our mass spring system, we can define a per tetrahedron kinetic energy using the generalized velocities of the jth tetrahedron, here denoted q sub j. And last video, we learned that q sub j can be reconstructed from the full q vector using an element selection matrix. We will use selection matrices pretty heavily from this point onwards, so it's a good idea to review the previous lecture if you feel a bit unsure about them. For our mass spring system, our element selection matrix selected the endpoints of our spring from the large Q matrix. Here, we build a selection matrix E sub j that selects the jth tetrahedron's 4 per vertex velocities. We can substitute this into our per element kinetic energy, and as always, the kinetic energy of our whole bunny is just the sum of these per tetrahedron kinetic energies. Again, because q dot is not indexed by j, we can take it outside of the sum over the tetrahedra. What remains inside the brackets is the full bunny mass matrix. From the previous video, we know that this element selection matrix sandwich means we need to assemble M in the same manner as we did the stiffness matrix in the previous lecture. This gives us a big but sparse 3n by 3n mass matrix, where n is the number of vertices in our mesh. Now that we have our kinetic energy, we're going to need to compute our potential energy. For our mass spring system, we defined a measure of deformation called a strain, and then we used this strain to create a potential energy function. We are going to do the same thing for our finite element bunny, but it's going to be a bit more involved. Now, as usual, we'll start by looking at just a single tetrahedron in isolation. We've already built a mapping from the reference state of a tetrahedron to its deformed state in the world space. What we need to do is come up with a way to quantify this deformation. To build such a tool, we're going to need to take a step back and consider a simple block of elastic material. Now, because this block of stuff is a continuum, any 2 points differ only in their position. Let's choose two arbitrary points on the reference configuration and connect them with a spring. Now we can look at the deformed block in the world space and see how this spring has deformed. Remember, these points were chosen arbitrarily. Choosing two other points gives us a different spring. It's like this whole block of material is filled with infinite springs moving in all directions. Represent this spring using a vector between our points. In the reference space, our vector runs from capital X sub 0 to capital X sub 1, and we're going to call this vector delta capital X. Each point in the reference space is deformed to a new position in the world space, which gives us a new vector delta X. Let's write out the formula for delta X explicitly. Looking at our diagram, we can see that capital X sub 1 can be expressed as capital X sub 0 plus delta capital X. Now what do we do whenever we see a function being evaluated at some offset position like this? Well, we Taylor expand. Conveniently, several terms cancel out, which means we can express delta X using the gradient of world space position with respect to reference space position. This gradient gets a special name. It's called the deformation gradient because it measures how an arbitrary vector in the reference space is deformed into the world space. Typically, this gradient, a 3x3 matrix in 3D, is represented by capital F. We are going to use this deformation gradient to build our strain. The strain we use will be a little bit different from the mass spring strain. We're going to quantify strain as the difference between deformed and undeformed lengths squared. We can express these length terms in terms of our vectors delta x and delta capital X. Next, we use the fact that delta x is equal to the deformation gradient times delta capital X and factor. Now remember, delta capital X is any vector in the undeformed shape. This formula shows us that deformation of all these random vectors is determined by this matrix term, which we call the green Lagrange strain. This strain measure is constructed using the deformation gradient transpose times itself, which has a special name, the right Cauchy-Green deformation tensor. Let's contrast this with a mass spring system, which had a scalar strain measure. Our finite element approach measures strain in all directions, and this manifests itself as a 3x3 matrix-valued strain measure. Like our mass spring system, we can now use this strain to compute a per tetrahedron potential energy. Just like with kinetic energy, we can start by looking at the potential energy of a single point in our tetrahedron. Here we introduce a special function psi, the strain energy density, which converts deformation gradients to potential energy per unit volume. Now there are a lot of choices for strain energy density function. Whole branches of science are devoted to defining these functions in a way that they reproduce the behavior of real-world materials. Practically, we either derive strain energy density ourselves or look up an existing formula in a paper or on Wikipedia, and here we're going to do the latter. One of the most popular choices of strain energy density is the Neo-Hookean strain energy. It is designed to mimic the behavior of certain rubber-like materials, and it's extremely popular in computer graphics and physics-based animation. Once we choose a strain energy density function, we can integrate it over our tetrahedron to get the per tetrahedron potential energy. However, we are missing an important piece of the puzzle if we want to evaluate this integral. We need to know how to compute f for our tetrahedron. Now, we know it's a derivative, but we never worked out the exact formula, so let's do that now. We already have a formula for the deformed position as a function of a point in our undeformed tetrahedron. And this formula uses barycentric coordinates as shape functions. A little bit of rearranging us a relatively compact matrix vector equation that expresses this relationship. We put reference positions in on the right, and deformed world space positions get computed on the left. Here, we use a vector of 1s to sum together all the rows of T inverse, which we use to compute phi sub 0 from the other shape function values. Now, we can compute the deformation gradient, which just asks that we take the derivative of this function with respect to capital X. The linearity of this function makes this pretty easy, and we end up with the following. Here we see that this gradient is constructed by multiplying a 3x4 matrix of deformed vertex positions with a 4x3 matrix, yielding a 3x3 deformation gradient. In fact, our 4x3 matrix is the derivative of our shape functions with respect to the reference coordinate. Importantly, the deformation gradient is constant for each tetrahedron. Now we can substitute our new deformation gradient formula into this integral. Remember, it's constant, so we can evaluate this integral multiplying the strain energy density evaluated using F by the volume of the undeformed tetrahedron. This is really a simple form of numerical integration, a single point numerical quadrature. And now, we use this per tetrahedron potential energy to build the total potential energy for the bunny. Alright, here's the per tetrahedron potential energy expressed using per tetrahedron generalized coordinates. As is becoming routine, we compute total potential energy by summing over all the tetrahedra in our bunny. Now we have kinetic and potential energy, we can build the Lagrangian, which looks like this. And next we'll do the same old, same old. We plug all this into our Euler-Lagrange equations, which surprisingly look the same as in the previous video. Remember, they aren't really the same. Our potential energy and mass matrix are different. This just highlights again the strength of the variational mechanics approach. As long as we can build our discrete operators and evaluate our respective energies, we can easily construct equations of motion for simulation. In order to complete our understanding of the finite element equations of motion, we're going to need one more piece of the puzzle. We need to know how to evaluate the right-hand side of the equations of motion, which are called the generalized forces. Computing our potential energy gradient is a little tricky because the deformation gradient for each tetrahedron is a matrix. Now, we can alleviate this problem by flattening F to a vector. That's going to look a little scary. Here we've taken our 3x3 deformation gradient matrix F and flattened it to a 9x1 vector. I've used a row-wise flattening here, but really any flattening will work as long as you're consistent when applying the following steps. Now we need to build a matrix that relates our generalized coordinates to our new vectorized F. To do this, we're going to need to bring back our shape function gradient matrix, which we will call D. Now don't panic. This formula looks really involved, but it's just the result of diligently churning through the linear algebra. This formula expresses our 9x1 deformation gradient matrix as the product of a 12x1 generalized coordinate vector for our tetrahedron multiplied by a 9x12 matrix. We call this big 9x12 matrix B, and when multiplied with Q sub j, it gives us the per tetrahedron deformation gradient. Returning to our generalized force formula, we can substitute in the vectorized deformation gradient, giving the following formula in terms of our full generalized coordinates for the mesh Q. This gradient is much more readily computable. Again, as we've seen before, we move the gradient with respect to Q inside of our sum, which we evaluate using the chain rule. Here, the derivative of psi with respect to flattened f is now a 9×1 vector. If we introduce the per tetrahedron generalized force, we see that this formula implies that our big generalized force vector is built by assembling the per tetrahedron contributions in exactly the same way as we did for mass spring systems in the previous video. And now we understand how to evaluate all the terms in our equations of motion. Integrating these equations will let us generate realistic simulations like this one of a human face. And with that, we come to the end of our introduction to finite element simulation. Next week, we will learn more about finite elements, including how to solve the equations of motion in a stable fashion, and how to use shape functions to improve the visual fidelity of our animations. As always, thanks for watching, and hopefully I'll see you all next time.